Hello and welcome to Field Notes on Climate Change, the podcast from the front lines of Arctic research, based at the Abisko Scientific Research Station in northern Sweden and produced in partnership with the Climate Impacts Research Centre at Umea University. I'm Emma, and in this episode I'm going to be trying to find some rubber boots in my size because I'm joining 3 different research teams to explore natural greenhouse gas emissions from lakes here in the Arctic. Now, we all know that often our energy generation, our cars and even our cows can be huge emitters of greenhouse gases. But here in the Arctic this summer, researchers are more interested in exploring where and how greenhouse gases like carbon dioxide and methane are emitted by natural processes. So I'm starting today in a place called Stordalen, where the permafrost is thawing and creating this landscape of shallow ponds. There's masses of carbon stored in the world's permafrost reserves. So what happens to that carbon when the permafrost thaws? I'm about to meet Marina Locke from Arizona State University, Ryan Sponsler from Umea University, and Katie Bennett from the University of New Hampshire, because today they are out in the field exploring how this carbon might be released into the atmosphere via the lakes. Okay, Marina, run me through what we're doing here today.
So we're measuring or collecting greenhouse gases that are produced in thaw ponds.
And why are we looking at thaw ponds, not regular lakes?
So thaw ponds are interesting because they are part of this permafrost network, so they're the result of thawed permafrost. So there's a lot more greenhouse gases that sort of are produced in these areas after the thawing of permafrost.
How are these gases produced in the first place? Where are they coming from?
Mostly from microbes in the sediment.
And before we get bitten alive by mosquitoes, I think we need to start doing some sampling.
Mm-hmm.
So what does that actually mean for us? What are we doing today?
So we're taking samples from the sediment water and from surface water. So we're taking water samples and shaking out the gas from those so we can take just the gas back to the lab.
Great. And if I'm looking at the pond right now, there's a kind of upturned bucket. Tell me what that's for.
So we call that a floating chamber. It has a CO2 sensor in it. So we're looking at it measures the flux of CO2 coming from the surface water into the air.
And the long pole behind it?
So that is a well. That is just to sort of simplify the collection of sediment water. So it's just basically a PVC pole with some holes in it, stuck about 10 centimeters into the sediment, so we can more easily take pore water samples. I'm just going to take this first bit of well water out.
Okay, so we're up to our ankles in the bog. You've got a syringe out. Explain to me what you're doing right now.
So right now I'm taking water samples through the well using this pore water sampler, and then taking some atmospheric gas sample, and then we're going to shake them. All right. I can take 2 of those too. Do you want to take the timer?
Let's put it on the ground.
Want to get on the shaking crew?
It's now a good time to find out that my boots aren't waterproof.
Are they not?
Nope.
Oh, really?
Okay, we're done.
We've got our water samples now, and we've drawn some air into the syringe, and then we've shaken those big syringes, for 5 minutes, which seemed a bit silly, but there is a purpose, isn't there?
Yeah, so the point of that is to sort of extract the gas from the water. So we're taking samples from pore water and from surface water, and the shaking kind of releases the gases, so we can take those gas samples, put them into vials, and bring them back into the lab in order to evaluate them for methane and CO2.
Great, and we're comparing samples taken from the bottom of the lake, but down by the sediment, and also from the surface water as well, aren't we?
That's right. So, one of the things we want to know is where are the gases being produced? I mean, is it all sort of sediment generated and moving vertically through the water column? Are there water column processes that also are producing greenhouse gases in ponds like this that have so much vegetation in them? That's an interesting thing to learn, basically. And then with the floating chamber, we can evaluate the flux from the water to the atmosphere.
You've got 16 total lakes that you're looking at out here in Stordalen, and you've chosen ones which have got very different vegetation covers. You've got mosses, you've got sedges, so grasses, and then you've got open water. What's the purpose of looking at different vegetation?
Yeah, so the reason I have 16 is there's 4 different groups. There's sedge-dominated, moss-dominated, a combination of sedge and moss-dominated, and then open water. And so what I'm partly interested in is looking at how these different types of vegetation can affect gas production. Mosses versus sedges, for instance, have very different sort of physiological, morphological traits that can affect not only how much gas is produced maybe in the system, but also how much of it is released, say, from sediment to surface water and ultimately to emitting into the air.
And what difference are you expecting to see, do you reckon, between the mosses and the sedges?
So one big thing I suspect is that there's the 2 different types of vegetation create different kinds of barriers. So, for instance, sedges have root masses in the sediment that could reduce the amount of gas that is released from the sediment into the surface water and ultimately into the air, whereas mosses create sort of a blanket that creates a physical barrier for surface water air exchange.
Fine, you've just thrown a probe for dissolved oxygen into the lake. Why are we looking at oxygen content?
So the oxygen availability in a lake is a really fundamental measure of the processes that are happening in the lake. Most organisms, including you and I, need oxygen. But there are a group of bacteria that can make their living without using oxygen. And some of those are microbes that, for example, produce methane. And methane, of course, may be in low concentrations, but it's a really powerful greenhouse gas. So understanding something about the oxygen level in these small ponds tells us something about whether we should expect to see a lot of CO2 produced or a lot of methane produced. And we learn something about the kinds of processes that are happening in the sediments, but in this case on the sort of lake bottom.
So in lakes where we're seeing a much lower dissolved oxygen concentration, we're expecting to see a higher production of methane?
That would be one expectation, yes. A small lake like this that has a lot of vegetation and a lot of sort of organic matter that's sort of accumulated on the lake bottom it's a really ideal place for the development of really low oxygen conditions and potentially high methane production.
Is that one of the other reasons we're really concerned about the future of these lakes with global warming kind of thawing out more and more of the permafrost and releasing more methane?
Absolutely, and people study methane production from permafrost in a variety of contexts. From the standpoint of a limnologist, or someone who works in water, we think about methane production from, in these lake bottoms as it relates to the other properties of the ponds. These ponds don't turn their water over very quickly, so it's easy for them to become anoxic or have low oxygen. People study methane production and loss from soils, also directly from the permafrost, which is that's not exactly what we're doing here. But yes, I mean, how the Arctic is going to produce methane in the future is something that a lot of people are interested in.
Pretty concerned about, I'm sure.
Yeah.
And what's this lake reading at the moment?
So right now, this lake is at only about 7% of oxygen saturation, so really low concentrations for a lake bottom, but also quite common for lake bottoms, actually, especially in the summer. It's not unusual at all to see this. So a lot of lakes will stratify, so they won't mix during the summer. These small ponds like this don't do that, which means that this low oxygen concentration is probably representative of most of the water, except maybe in the very surface. So this suggests that there could be some methane production happening. We'll find out when we run the samples.
One of the reasons we've come out here to Stordalen is actually it's one of the best places, especially in the Arctic, one of the most accessible places for scientists to study these peat bogs and these mires and these thaw ponds, because we've got this vast and open region of permafrost thaw. And all it takes is for me to look around and I can see so many different little research sites that are set up across these bogs and across these mires and ponds. There's climate stations and weather monitoring stations out on all of the lakes. There's a caravan with a lot of suspicious looking gas chambers next to it. Goodness knows what they're doing. There's flags everywhere with little red and yellow and green and blue markers. There's tubes coming out of every pond. We've got the gas chambers, which kind of look like upside down paddling pools. And although we can't see very many other people right now, you can really see how important this site is to science. And Ryan has just pointed out to me, actually, there's this huge, almost crack in the landscape just near where we've set down. And it kind of extends down a metre, so you can really see the layers of soil and see what's going on underground here in the patches, which aren't obviously ponds. And you can see how densely packed this peat is. This peat has locked away organic matter full of carbon for years. As the permafrost and the peat thaws, this carbon is then becoming accessible to the environment. So whether that's just going to be released through soil decomposition, or whether it's going to drain into the water sources and provide more nutrients and release more carbon through these emissions in these lakes. And that's why there are so many scientists here. That's why there are so many teams interested in looking at this, because we don't know the rate at which, or the amount at which, carbon could be potentially released from these areas, especially if with global warming and climate change, more and more of these areas are going to be thawing and continuing to release these greenhouse gases. So we know that Stordalen's a really popular place. There are loads and loads of researchers working out here, and one of the other researchers out here from Arbisco, from the research station, is Katie.
Hi.
Hello. Now, Katie, I wanted to come and talk to you because the methane emissions that Ryan and Marina are looking at, they're all in the water, aren't they? They're looking at the diffusion of this methane, but you're looking at the bubbles. How does your work add to theirs?
Yes, that's correct. So I study methane ebullition, or bubbling, from these thaw ponds that are out here on Stordalen. So I have multiple traps, bubble traps we call them, set up on 7 of these ponds, and basically it's just an upside down cone that creates a vacuum, and the methane is produced in the sediment of these ponds by microbes. So the bubbles of the methane then travel up through the water column, and I collect them in these traps. So it's another dominant form of methane production that we're seeing in these areas, which is not quite the same as diffusion.
And what are you doing once you've taken your gas samples? What happens to them then?
So I take the gas samples, I collect them in these little 10 ml syringes. You can see me walking around with a big plastic bag full of them, and I bring them back to the research station. And there I use a gas chromatograph to look at the concentration of the methane in my samples. And from there we're able to estimate the bubble flux, or the amount of methane that's being produced from these bubbles. And because we know the area of the cones, we're able to take that flux value and use it to estimate the amount of methane that's bubbling out of the entire pond. And then I also store a large number of these samples, and I bring them back to my university back in the US. And there I analyze the samples for the carbon-13 isotope, which is found in methane. And with that value, I get somewhere between a range, which is called the isotopic signature. And what the isotopic signature is telling me is what pathway the microbes were using. I like to refer to it as a recipe when I'm explaining it to people. So basically, if you think of methane like a cake, the microbes are either making vanilla or chocolate cake. And at the end of the day, it's still cake, it's still methane, but they're using a different carbon source to produce that methane, which is what we can determine with the isotopic signature.
And why are we interested in looking at these different versions of cake? You've got me in the metaphor now.
Yeah, so isotopic signatures are really neat. They can tell us a lot of different things, but specifically what I'm focusing on is with looking at these pathways and the isotopic signature coming from the ponds, it relates to global modeling of methane emissions. So the atmosphere has an isotopic signature that's different from the one that comes from the ponds, and that's because it's an average of all the different methane sources from things like cows or fossil fuel burning, as well as wetlands. And so right now, global models account for an isotopic signature that's coming from wetlands, but they're not accounting for any type of shift in that signature. And what we think we're seeing is a difference in the isotopic signature of the different ponds looking at. And so we're looking to see if over time, whether there's any sort of shift in that signature or whether it's remaining constant, in which case our global models would be correct. But if it's changing, especially as the Arctic continues to warm and more of these ponds form and they get bigger, maybe the microbes start using a different carbon source more dominantly. Maybe they're making more chocolate cake than vanilla cake. Who knows? That's what I'm trying to find out. So that's going to be really important to account for. And right now we have isotopic signature data from these ponds going back to 2012. And now it's 2019. So I just started this project as my master's project, but another PhD candidate in my lab has been collecting this data for quite a while. So it's really exciting. We have a nice stretch of time to be able to look at what's happening out here and sort of relate that to what's happening globally. And who knows, maybe we'll be able to scale this up to other Arctic locations, but for now it's just at Abisko.
Perfect. And like you said, this is the perfect place to be starting your research,
yes,
because we do have this amazing history and backlog of data from people studying these lakes.
Exactly.
So now that I've helped Marina and Ryan sample their lakes and I've caught up with Katie, that's actually it for my time here in Stordalen. But our journey through the carbon and methane emissions of lakes up here is far from over. I've got another team waiting for me at a different field site just a short drive away who are also investigating different ways that methane can be released from lakes. So I've arrived at my second site, and this time I'm joining a team of researchers from Umea University looking at boreal lakes in the west of Abisko as opposed to the thaw ponds that we were looking at in Stordalen. Now, we've heard a lot about the research into methane emissions coming from the microbial communities in the lakes and the impact that different vegetation might have on these levels. But some of the methane emitted by lakes can also come from elsewhere and can be transported into the lakes from groundwater. So Karolina Olid, assistant professor at Umea University, and her team are looking at this. So Karolina, it's a lovely sunny day. We're sat just next to the lake. Tell me, what is it we're actually going to be doing here and why are we looking at these lakes in particular?
Yeah, so we are going to sample today 2 lakes, and our main objective is trying to know how much groundwater is discharging into the lakes. Is all this water that goes under the ground and we don't see, but of course is reaching these lakes. And what we are going to do is measuring one element that is enriched in this groundwater. We have really high concentrations of this element in groundwater, but not in lakes. Mm-hmm. And this is radon. Uh-huh. And then what we are going to do is measuring radon in the lake, in several points of this lake. And also we will measure radon in the inlets and also the outlets. So the water that comes into the lake and also the water that flows out from the lake. And the idea, knowing all this, we can calculate how much groundwater comes into this lake, and then we will measure how much methane comes with it. And this is important because, as some studies suggest, that the main source of methane is internal processes within the lake. There are other studies that suggest that no, that it's more external processes and mainly groundwater that brings a lot of methane. And this is what we want to test to prove in this project, if these lakes are getting important amounts of methane from the catchment and how much this is important to control methane emissions from these lakes.
Great. And you said that you're using radon as the tracer, the naturally occurring radon in the soil, which can come in through the groundwater. What makes radon itself a particularly good kind of tracker or tracer element?
So radon is a radionuclide, meaning that it decays. So if you have a concentration today, tomorrow you will have less concentration. Mm-hmm. So, and the advantage of using radon is that we know this rate, so we know how fast it decays. So it's like having an internal clock, like a chronometer, and then we can estimate time. So there are other tracers we could use to trace groundwater, but they will only tell you, okay, you have here groundwater, but using radon, as you can calculate time, you can estimate fluxes and liters per day or liters per hour. So this is a huge advantage of using radon, plus also it gets enriched in groundwater.
And how much of a contribution do you think groundwater could make to the level of methane that's coming out of lakes as a whole?
Okay, well, there is one study in Alaska that suggests like maybe 50% of the emissions. Now I don't have the numbers here, but then I sampled 3 lakes up here in Abisko last year, and then I saw that maybe the contribution can be as important as other internal processes. So it might be a process to take into account. But of course, I also saw that I sampled 3 lakes, and I saw a huge importance of groundwater in one of them, but not in another one. So the point of this sampling this year and sampling 10 lakes is to see special patterns. So see if all the lakes behave in the same way, or we can see like lakes at higher altitude, maybe they get less groundwater, or maybe with different slope, with different depth. So this is also the point, because there is no study comparing different lakes in the same location, and we want to see spatial patterns and also temporal patterns, because we will sample through the season, now in July and also in September, and then we will see also if there are differences between seasons. So the point, one of the objectives is seeing lakes in different locations behave similar, and also in June is the same, well, July is the same than in September. So both spatial and temporal variability.
Great.
Okay, Emma, it's nice having you here, but of course you have to work a bit. So now you will join me in the field, right?
Absolutely. I think we need to go get on the boat.
Yes, let's go.
Brilliant.
See. Thanks.
Yeah, we are ready.
We are here? We are here?
We are here.
Here, okay.
Yes.
So we have 2 stations, one there and one there, okay? So we're rowing to get the position, okay? So you're... Yo tenía un jardí florir y un saltapar. Yo tenía...
Okay, we're in position, we're on the lake, we're surrounded by quite a lot of tubes and some giant old Coke bottles. What are we doing? Talk me through the process.
So now we are collecting lake water samples in these cola bottles to measure radon, because we know that cola bottles keeps the gas, and radon is a gas. So that's why we collect the water samples in these Coca-Cola bottles. But also we collect small vials to measure the concentration of methane in the lake. And we will then, in the lab, we will process the samples, and then we will estimate how much methane comes from groundwater.
Brilliant. Okay.
Yeah, you can write down.
You can write
I'm on
And
writing
I will-
duty.
and I
and the
will-
number and the time. Do you have a clock?
I've got a watch, yes.
Okay. Which number is this one, Jordi? I'll sing.
Think.
You have to write number 5
Yeah, there is wind, so we need the anchor.
and the time when we start sampling. Station 1.
Station 1. ¿Está puesta la hora? 76.
So I've been out on the lake and I've been out sampling some of the waters in the lake. Valentin, you're doing the groundwater samples. Tell me how that works.
So basically what we are doing now, we stick a metal stick into the sediments, and basically it has a screen at a depth that we want, and then we have a vacuum pump and we collect the water. We basically pump the water so we can collect the water that is within the sediments at the depth that we want.
Perfect, so like a big straw.
Like, yeah, it could be like that. Yeah, it's a good example.
Great, and once you've done all of that, they go in your backpacks and then you carry them back to the car and back to the lab.
Yeah, the advantage of that is that since we are collecting pure water, we cannot pore water, that is basically the water that is within the sediment. So we cannot collect huge amount of water because otherwise we will mix it with the surface water. So the main advantage is that we are just collecting small, tiny bottles, so we don't have to carry a lot of weight.
I see now why you volunteered to do groundwater
that's
and
a
not
good
go on
one.
the lake.
Yeah. So when because we're doing this sampling of interstitial water, but we'll do also the sampling of inlets and outlets. So basically all the streams that are flowing into or out from the lake. So we need also to quantify them, to know the volume of water that is entering or going out, and also measure the concentrations of all the parameters that we are analyzing.
Okay, great. Well, we've got all of our samples now. We've just got to carry them back to the car and then back to the station. What happens next? What happens when you get the samples back to the lab?
Well, here we have collect samples to measure different things. So some of them will be just acidified and then keep in the fridge. And then the most important thing we have to do now, and we have to be fast, is measuring the radon in the bottles, because radon decays quite fast. In 3 days, you have half of the concentration we had in the field. So then we measure with one special detector that just make bubbles, and we measure these bubbles. And then the machine just will tell us how much radon this water has. And we can quantify then how much groundwater came into the lake.
Brilliant. Well, before I let you get on with that, this was one last question. Do you think there's anything that we can do to kind of slow or reduce the rate of methane that's being lost from the Arctic?
Yeah, this is a really important question, and I don't think I have the answer. But what we as researchers, I think we need to try to understand how this system works. But then I think it's more policymakers and try to develop strategies to mitigate these emissions. And for example, in our case, that we want to see if there is special patterns for these emissions, I think developing policies to managing the land would help a lot on trying to reduce these emissions.
So there we have it. Today I've gone out with 3 different teams, 3 of them many who are exploring methane emissions up here in the Arctic from the lakes. But there are many more researchers asking much the same questions about how much carbon in the Arctic could be released into the atmosphere and how it might happen. The more we learn about these systems and how they work, the better we can make our climate change prediction models, and then hopefully the more accurately we can plan for our future. So that's it for this episode. Thanks for listening. I hope you enjoyed wading through the lakes and thaw ponds of Arctic Sweden and trying to understand a little bit more about natural greenhouse gas emissions up here. Don't forget to hit subscribe so that you don't miss any of our upcoming episodes, and please do leave a comment or 2 to let us know what you think. If you've got any questions or you want to get in touch, you can tweet the Climate Impacts Research Centre at Arctic Circ, reach me at Emma Brisdian, or check the show notes for other ways to get in contact. I'll see you soon for another episode of Field Notes.